Hey everyone, welcome to our project presentation video. Our project was a fraudulent transaction detection system. In this video, we're going to be talking to you about, just the details of our project, and we're going to be walking you through our flow, right? To begin with, here's just a brief overview of our project. We're going to be walking through each of these points briefly and showing you our results as well. Right. So as a description of our project, in our fraudulent transaction detection system, we aim to develop a robust and scalable system to detect and prevent fraudulent activities within financial transactions. By leveraging the power of big data technologies, we have analyzed large volumes of transactional data, to identify patterns, anomalies, and suspicious behavior, which are usually indicative of fraudulent transactions. We've also, utilized several machine learning algorithms and also in this case, Airflow to automate the intelligent detection of fraudulent transactions. Now, moving on to the business value and social value of our project, fraudulent detection systems offer, I would say, a significant business value to individuals, companies, and financial systems by protecting them against fraudulent activities. As we can see over the past few years, there's been a substantial growth in transaction volumes. Just as an example, PayPal processed 6.2 billion transactions in the third quarter of last year, or if this year, 2023. As we know, financial fraud poses a significant challenge across a variety of industries. All people from all walks of life are affected by financial fraud, and right, exactly, and it results in significant economic losses each year. One main aspect is also erodes the trust in financial systems, and eventually, data-driven methods have come about and they've revolutionized fraud detection. Moving next into how we've approached the problem. Given the large size of our data set, we have about 1 million points of data and 400 features. For the purpose of this demonstration for our project video, we've used a static data set, but our project is adaptable to be used for a dynamic data set where fraudulent data, where the transaction data can be accumulated and then worked on by the model. So yeah, so we have a static data set. What we essentially did was once we had a data set, we generated HTML and JavaScript dashboards using d3.js, to basically visualize the raw data and see what we could work with, some sort of feature engineering. Moving into the pre-processing steps, once we had basically visualized the data, analyzed it, we went about different kinds of pre-processing methods, dropping of features, dealing with imbalanced classes, using standard scalars. We experimented with PCA, and we found something interesting that we'll talk about later. But yeah, Airflow, and then we also used Airflow to design the workflow, for parallel model training and evaluation. And yeah, given that, we generated a visualization to compare how the models performed on our data. Right. Now, moving into the system architecture, our system architecture is fairly straightforward. Given the fraud detection data set where we have our data set from Kaggle in this case that we have that we get. So once we have obtained the data set, we go into the exploratory data analysis and data pre-processing, where we have, again, dealing with the imbalanced classes, etc. So once we have our prepared data, the data is passed into 7 of our models, varying from, as you can see, KNNs, logistic regression, MLP, naive Bayes, random forests. Each of these models are run parallelly, and ultimately when the results are generated, we compare the models. Now, since for the project, we're going to be running all 7 of these models and implementing this system architecture on Airflow, I will be demonstrating, the graph on Airflow as well. So yeah, so this is, the DAG for our Airflow implementation. As we can see here, running all of the models in all of the steps in the system architecture has taken us some time. So it takes roughly about 6 or 7 minutes. So I will be triggering the DAG now, so that, by the end of this presentation, we can see, hopefully the results have been generated. So I'm just going to trigger the DAG. Yeah, so this is what I think the graph of our system looks like, similar to system architecture, but yeah. Moving on, I think Rufina will be presenting or talking about the data.
So the data set that we used initially was different from the one that we have on this slide. This was recommended to us by one of the TAs. It was also taken from Kaggle. The data was compiled by Vesta using real-world e-commerce transactions. And we use about 1 million data points, about 600,000 in training records and 500,000 in test records. And we have two kinds of data files for training and test: transaction and identity. Transaction contains data like transaction amount, continuous numerical data, data relating to the credit card type used, or a debit card, or MasterCard, Visa, Discover, those kind of features. Identity focuses on where the transaction has happened. So you might have like a device ID or an operating system name or even a browser name in some of the columns. And in total, combining both of these data files for each of the training and test records, we have in total 434 features, and our target variable is fraud. Since we have two different data files, we had to combine them on the basis of transaction ID, because that's the only common column both have, and that helped us merge both the data sets together to form one entire table. We faced a lot of issues with understanding the categorical data here, since even though this data is labeled, the column names are not very descriptive of what kind of data they contain. So if you see maybe like ID 31 or something in one of the files, that could be type of card being used, but you wouldn't know unless you go into the data file and have a look. So we spent a lot of time manually sifting through the data and understanding what is there. Coming to the three V's of data, for the first V, volume, we have approximately 1 million data samples obtained from Kaggle, like I mentioned before. Velocity, we have static data. Since you can't really obtain real-time fraudulent data, you need to have it labeled so that the machine learning model can understand what kind of data is actually fraudulent data, and real-time data is not really applicable for that. Coming to variety, we have pretty structured data with 400 plus features with labels. Even though the labels are kind of rudimentary, it's still structured. Moving on to the next slide. When we were doing exploratory data analysis, we realized that most of our data is full of NaN and null values, and some columns were even dominated by certain values. According to our references on Kaggle, 0.9 was the best threshold to use. In the sense, 90% of the data being NaNs means that we can drop the data. That made us drop around 84 columns when we had our first run through. But due to the lack of resources, we experimented with different thresholds so that we would be able to actually run our project and our system. And we settled on 0.7 as the threshold, and we had to drop around 350 columns. We also performed correlation analysis and found that two columns were related, transaction DT and transaction ID. So we just dropped one of them and continued. Another thing that we decided to do was take time into consideration. Since we have different sets of files for train and test data, when we were looking at the time feature, we realized that all the transaction details in the train file and all the transaction details in the test file have completely different timestamps. There's no overlap, which made it sensible for us to use time as a feature while training instead of dropping it, so that we can apply our system to dynamic real-time data as well. Moving on to the next slide. Yeah. We also decided to build a couple of dashboards using HTML and D3.js. We used two different kinds of charts to analyze our data. We used histograms for continuous data and pie charts for categorical data. This helped us realize that most of our data is highly unbalanced, and it also helped us visualize what percentage of the data contains a certain label or what percentage of data is valid for us to use. We made a lot of conclusions from this analysis, and we had separate dashboards for transaction and train identity. Vishal will go into some more results from this.
Yeah, so moving on to how we implemented pre-processing for our data set. So as Rufina described, we used a 70% threshold to drop null values and and features where a single value dominated that feature. We also explored correlation analysis, and however, when we used 70% threshold, we didn't find any significant correlated features, except the two that Rufina described. But when we use the advised threshold of 0.9 for correlation, we realized that 38 columns can be dropped. After that, we further moved on to reduce to drop some data points or records where we still encountered NaN values. After that, we in our data set we also encountered class imbalance in the sense that roughly 3.5% of the data set was classified as fraud transactions, whereas the remaining was a fraudulent transaction. To tackle this, we tried two techniques, undersampling and oversampling. In all the three cases of reducing our data set and using oversampling, we encountered out-of-memory errors. For just because of this, in order to run a pipeline successfully and to get a reasonable result, we went ahead with undersampling. Following that, after with balancing our data set, we used a standard scaler to scale the features to bring them all around a similar range. We also experimented with PCA and we tried with different basically principal component values from 20 to 50. And however, like in all of these cases, we observed a significant drop in performance and accuracy scores. So in a final implementation that my friend Vishnu has triggered here, we are not using any PC as such. We are going ahead with just, I think, 70 to 80 features that we have after all the pre-processed data. Next slide, please. So moving on to the machine learning algorithm selection, we used 7 algorithms. The first one being k nearest neighbors. The motivation behind choosing k nearest neighbors was to estimate a reasonable baseline. And for all the other models that we have chosen, we basically targeted a few features, which is like, since our data set is huge, we need them to be computationally efficient. They should be able to handle significantly large data sets and even handle high dimensionality. So, and towards the end, we also included random forest and XGBoost, especially because they are ensemble methods where they use multiple decision trees to generate the final decision, and they are very efficient and very fast in their performance. Moving on to the next slide. In the model comparison, we found that it was expected, but yeah, XGBoost to outperform other models, especially for accuracy and F1 score. And we found that XGBoost also followed closely second to random forest in terms of precision, which is a very important metric in the financial fraud detection problem. Something we didn't expect was SVC to take a lot of time. And even in the results, we observed that the performance metrics were not up to the mark, and we would strongly advise not using it. Moving on to the next slide. Yeah, this is our review. Basically, we have we achieved all the milestones as decided before starting the project. Next slide. Yeah, I think Vishnu can now present our progress on Airflow.
Right. Thank you, Vishal. Yeah. So now, before Rufina and Vishal finish their sections, we had triggered the DAG. We can just check in on that. Right. So as we can see, the DAG triggered and took us roughly about 4 minutes to complete, which is quite quick. We can see that from the Gantt results here. Right. So as we can see here that our implementation was successful. We have like a graph here as well that shows, all of the models ran successfully, starting from the data fetching and preparation, passing the data to each model. And then we had, of course, running of each of the models. Each of the models generated their, their accuracy scores, and we compare them towards the end. Yeah, so, as we can see here, this is our results, and the project was successful. Rufina and Vishal, do you guys have anything else to add, or?
Yeah, I will present the dashboards that we created for brief.
Sure. Should I stop presenting?
Yeah, I think you need to enable screen sharing. Okay. So yeah, these are the dashboards that we created. This one is pie chart for the identity files, and it's a dynamic pie chart. Basically, we could choose any other column for representing the data distribution. This is for the transaction document. Again, we have multiple features that we are trying to illustrate. Okay. Moving on to continuous data distribution, we are basically using two features, the transaction amount and the transaction date, and even the number of pins that we are presenting is dynamic. So for example, I could do something like this, and yes, as you can see, it's pretty fast and works accurately. So I think, yeah, that's all from our side. Thank you.